Everybody, it's Tyler here at the official Week 0 check-in. Team number 125 NUTRONs, last year division finalists. This year, 3 district events coming up. We're so excited to see. Look at this incredible machine they built here once again. It's so compact, it's tiny, it's cute, I love it. This robot here, we just saw it perform on the field, looking great. And the expectations we have, many of us have amongst 125 as well. Help me talk more about this robot, by the way. I have Clemens, Sarah, and Zarias. And of course, we'll be following up. They have a really cool cube intake. We'll showcase that arm, their claw, talk a little bit about programming, all here coming up on Behind the Bumpers. This video on First Updates Now is made possible by viewers like you and also the following sponsors. If your team is using SolidWorks, make sure you log into the 3D Experience platform to gain access to tutorials, collaborate with other users, and download the ChargeUp field and kit up parts. Go to solidworks.com/first and click on Log into 3D Experience platform to gain access. FRC Premiere Night is back on Saturday, February 25th. Submit a unique video showcasing your team's charged up robot progress by Thursday, February 23rd at First Updates Now/Premiere23. Premiere Night is a great way to engage with the community. Get more information and submit your video at firstupdatesnow.com/Premiere23. Let's start out with that cube intake you guys were talking about. This is so cool. I'd love to see this come out so we can showcase a little bit, but talk to me about how you came up with this and just some of the strategy behind it in regards to the intake.
Yeah, so one of our priorities this year was we wanted to build a robot that was like very simple and robust. And we kind of identified pneumatics as a failing point, and also something that's just difficult to control. So we decided to go with a rack and pinion system to control the extension, which is something kind of novel. We also have a split intake. So the two sides of the intake are cantilevered.
Yeah.
And that allows us to drop our arm all the way down in a resting position. Currently in match, we're stowing it at kind of our scoring set point, but we have the ability to drop it all the way down in between the two intakes. And that really drops our center of gravity super low so we can zip around the field.
Can we see that intake come out? I'd love to see like a cube come into your robot. So that's just so smooth. I love the idea of that split intake, by the way. Did you have any, when designing it or actually doing any testing, did you have any difficulties with having kind of two separate systems there?
So one of the things that you can see is that it's linked by a hex shaft all the way across.
Oh,
so
yeah.
It's all powered by one motor controlling the extension. And so that means it's very robust, so they don't desync from one another. The couplers do make it easy, though, if we want to work on one side or take one side off the robot and change parts out. So yeah.
Let's keep moving up in your robot here. We'll talk about this pivot and your arm into it. I know Sarah's got another iteration of this as well, too. Everything's just so compact with this. I love just the overall design. Talking about how you came up with this sort of design for your robot.
Yeah, so going back to one of our priorities being to lower the center of gravity, we wanted the arm to be as compact as possible. So in CAD, we quickly realized that we're going to need 3 moving stages, and we wanted to do a telescoping arm. So that's kind of something that was pretty new for us. And so this is what we came up with. It's a 3-stage cascade rigged arm, all powered off of a Neo. And it's all on a chain pivot, which is also powered by a Neo. And yeah, so this caused a lot of trouble, but it's also pretty cool. The 3D printed bearing blocks are fully custom, and everything is packed super, super tight. The gaps between the tubes themselves are very small, so in order to fit everything in there, we have to do a lot of design work and iteration, but yeah.
On this pivot here, when you're looking at it from the design-wise, how did you end up packaging this so it was just right for your team?
Yeah, so one of the things that we had to consider is the rule this year that you can only extend from one side of the frame. So that informed kind of the pivot placement, because we wanted it towards the back of the robot to maximize the effective length of the arm that we could stow. And so that those two factors kind of informed where the pivot was. In terms of the actual design itself, it was really just about packaging the reduction as efficiently as possible. And so that's why the gear train loops from this side of the arm underneath via the hex shaft and then comes up on the other side. And that way it's all nested very tightly underneath the arm.
Can we see your arm come out and kind of demonstrate that on the actual robot? So from scoring positions wise, I think we'll talk about maybe programming a little bit later as well too, but like, how did you, when you were looking at scoring, some teams are shooting kind of the last set. Your team looks like it's able to just reach all the way over.
Yeah.
Why was that important to your team?
Yeah, so one of the things that we also identified is that we want to have a little bit of flexibility. So say we're not aligned completely straight, we have the ability to have a little bit of overshoot. And so that's why we were able to extend so far. Also for week 0, obviously we haven't tuned quite the place and shoot yet. So for us, placing is the most repeatable right now, and we have the ability to do that because we have such a fast and long arm.
Sarah, I really want to talk about this wicked wrist that you have here on your robot, and of course we'll talk about your claw as well too, but take a look at this 3D printing that's on this. I love this so much. Talk to me about how this design came together, and then we'll keep moving on into your claw as well.
Okay, so on the NUTRONs, we have a series of like SolidWorks documents we can use to generate parts like this for like herringbone gears, straight cut, I forget what it's called, the ones that are one angle all the way across as well. And what we'll do is we can choose like pitch, the tooth count, all those sorts of things, and then export it into a model of its own and slice it apart as we need. You can see this one isn't a full gear all the way around, and it slots onto this final piece here on the arm.
As we keep moving up into your claw here, how does this kind of all come together for you? And then I got to ask, for NUTRONs, when I look at previous robots, you tend to have had extremely wide intakes, similar to what you've had here as well. But with that handoff, I'm assuming that's not as important, but how did you tackle that in regards to the cone itself and finding that, like, hey, like we don't need to have a super wide intake for the cone?
So in regards for the cone, at the beginning of the season, we were working on a prototype based on an old YouTube video we found of a machine that picked up traffic cones off the road.
Oh, cool, yeah.
Yeah, on a way to like automatically orient it by having different parts of the cone hit different bars. We eventually ended up tabling that because we wanted to focus more on the main aspects of our robot for doing something so fancy. And so we then arrived at the idea of mainly just intaking cones off of the shelf, and we're able to very easily do that.
On this overall claw here, when you look at talking about how you end up spacing your wheel configuration, like is that just strictly for the cone itself to try to get a good grip on it?
So in terms of wheel spacing, these are mainly driven by two things. Well, I suppose three things rather.
Sure.
We wanted to have this, first of all, be as compact as we could possibly make it. We also wanted to, of course, be able to capture the cubes and the cones over the center line of the wheel. So they wouldn't, so instead of pinching the very edge of something, you have it captured all the way in. And the final constraint was we wanted to use as many parts that we had in the lab as we could. For example, all of the belts and gears on this came just straight out of parts bins. And another major constraint, or another design decision along that route, was we wanted the entire thing, as I said earlier, to be as compact as possible, as well as lightweight, which is why it is almost entirely made out of 3D printed parts with Lexan parts, as you can see here. There's also an additional version that we've theorized about, maybe replacing these polycarbonate sheets here with some thin carbon fiber ones, laser cut.
When I was talking to your team earlier, I think you said this whole robot right now is like 78 pounds, right?
Yep.
So yeah, obviously extremely efficient on the weight ratio for that. A low COG as well too. I love it so far. Let's wrap up on your robot. Head over to Zarias. You can talk more about some of the programs going to. I can't imagine like all the systems that have really made in this robot, try to get all the different positions right and that sort of thing. So talking about some of the aspects as a programmer on this team, what you've had to work with for this robot.
So the first thing is obviously the swerve. We had to implement the turning and driving, and we spent a lot of time tuning that, especially when new modules were added on top with the new weight. The arm also is very difficult with the pivot, because as the arm extends, the force of gravity increases because the radius is greater.
Yeah.
So we had to change the pivot power based on the extension of the arm.
When you're looking at from autonomous-wise and approaching this game, what are kind of the key aspects your team is looking at doing for auto this year?
So the auto, the first thing is we start backwards and we dunk the cone on the first peg, it's super fast and it gets us 6 points. And then our next plan is to get another cone and store it right next to it, so we're ready for the link. And then right now we're going straight to the balance, but eventually we want to do a 3 game-piece auto.
Looking forward to seeing that for sure. For your balancing, last thing I want to ask you, is your team looking at doing any sort of auto balancing or anything like that?
Yeah, we're looking into using the gyro to look at the yaw and pitch to balance and help the driver in the process.
Well, 125 NUTRONs, really appreciate you taking the time. Absolutely phenomenal machine that we've seen here so far.
3 district events coming up, a lot of opportunities to keep improving and making this robot a top tier one that we see every single year. So thanks a lot for taking time, and good luck to your team.
Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. If your team is using SolidWorks, make sure you log into the 3D Experience platform to gain access to tutorials, collaborate with other users, and download the Charge Up Field and Kit Up parts. Go to solidworks.com/first and click on Log into 3D Experience platform to gain access. FRC Premiere Night is back on Saturday, February 25th. Submit a unique video showcasing your team's charged up robot progress by Thursday, February 23rd at firstupdatesnow/premiere23. Premiere Night is a great way to engage with the community. Get more information and submit your video at firstupdatesnow.com/premiere23. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.